There is a star dying right now, 15,000 light-years from where you are sitting. It is not dying quietly. It is not fading gently into the void. It is tearing itself apart, shredding its own body, and flinging the pieces into the darkness of interstellar space at speeds that would cross our entire solar system in a matter of hours. Every single second, this star loses mass equivalent to the weight of the entire Earth. Not every year, not every century, every second. And it has been doing this for tens of thousands of years. The gas and dust it has expelled now form a cloud stretching 6 light-years across, a luminous shroud of matter that once burned at the heart of one of the most violent objects in our galaxy. 6 light-years. That is roughly 1.5 times the distance from our Sun to the nearest neighbouring star. This single dying star has filled a volume of space larger than the gap between solar systems with its own expelled flesh. The name of this star is WR124, and in 2022, the James Webb Space Telescope turned its golden mirror toward this dying giant and captured an image so detailed, so rich in scientific data, that it forced astronomers around the world to rethink fundamental questions about how massive stars die and what they leave behind. The image was released publicly in March of 2023, and it swept across the internet in hours. People shared it for its beauty. Scientists studied it for its implications. Both groups were right to pay attention, though for very different reasons. But beauty is deceptive. What looks like a delicate watercolor painting in infrared light is, in reality, one of the most energetically violent events happening in our region of the Milky Way. The nebula surrounding WR124, catalogued as M167, is not a gentle cloud. It is a shockwave made visible. It is the exhaled breath of a star that has already shed more than 10 times the mass of our Sun. Material flung outward at speeds exceeding 150,000 kilometers per hour. That is fast enough to travel from the Earth to the Moon in less than 3 hours. Fast enough to cross the continental United States in under a minute. And the star is not done. It is still shedding, still losing mass, still racing toward an end that, when it comes, will outshine entire galaxies for a brief blinding moment. WR124 is a Wolf-Rayet star, a class of stellar objects so rare that fewer than 600 have been identified in our entire galaxy out of an estimated 400 billion stars. That means for every Wolf-Rayet star, there are roughly 700 million ordinary stars. If stars were people, Wolf-Rayet stars would be rarer than one person in the entire population of Europe. These are not ordinary stars. They are stellar monsters, born with masses 30, 40, sometimes 60 or more times the mass of our Sun. They burn through their nuclear fuel at a pace that is almost incomprehensible. While our Sun will live for roughly 10 billion years, a Wolf-Rayet star may exist for only a few million. In cosmic terms, that is less than a heartbeat. If the age of the universe were compressed into a single calendar year, a Wolf-Rayet star's entire existence would begin and end within the first few seconds of January 1st. What the James Webb Space Telescope revealed about WR124 was not merely a stunning portrait. It was a window into a process that governs the very chemistry of the universe. The dust being created in WR124's nebula is the same kind of dust that eventually forms planets, moons, and the building blocks of organic molecules. The carbon in your body, the oxygen in your lungs, the iron in your blood, the calcium in your teeth. All of it was forged in the hearts of stars like this one and scattered into space during exactly this kind of violent death. We exist because stars like WR124 once died. That is not poetry. That is not metaphor. That is measured, verified, peer-reviewed astrophysics. By the end of tonight, you're going to understand what Wolf-Rayet stars truly are, why they matter far more than their rarity suggests, what the James Webb Space Telescope actually revealed when it peered into the nebula of WR124, and why this single dying star is forcing us to rewrite chapters of astrophysics we thought were settled. You will understand why some astronomers believe WR124 could become one of the most scientifically valuable supernovae our instruments ever witness. And you will understand why the dust surrounding this star, invisible to human eyes but blazing in infrared wavelengths, holds secrets about the origins of planets, organic chemistry, and life itself. The answers are more unsettling than you might expect, because the story of WR124 is not just the story of one star. It is the story of every atom of carbon, oxygen, and iron in the universe. It is the story of how the cosmos, starting from nothing but hydrogen and helium, built the entire periodic table, element by element, death by death, explosion by explosion. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand what is happening to WR124, we first need to understand what a star actually is. Not in the poetic sense. Not as a twinkling point of light in the night sky. A star is a sphere of plasma held together by its own gravity, sustained by the energy released from nuclear fusion in its core. Hydrogen atoms are squeezed together under unimaginable pressure and temperature until they fuse into helium, releasing energy in the process. That energy pushes outward against the crushing weight of the star's own mass, creating a balance, a tug-of-war between gravity pulling inward and radiation pressure pushing outward. This balance is called hydrostatic equilibrium. It is the reason a star does not collapse under its own weight. It is also the reason a star does not simply explode. As long as this balance holds, the star lives. When the balance breaks, the star dies. Our Sun is a modest star. It has a mass of roughly 2 nonillion kilograms, which is a 2 followed by 30 zeros. It is about 1.4 million kilometers in diameter, roughly 109 times the diameter of Earth. If you placed the Earth next to the Sun, our planet would look like a small marble beside a beach ball. The Sun's surface temperature is approximately 5,500 degrees Celsius, hot enough to melt any known substance. Its core temperature reaches about 15 million degrees Celsius. These are enormous numbers by human standards, but by stellar standards, the Sun is unremarkable. It sits in the middle of what astronomers call the main sequence, a classification of stars based on their mass, temperature, and luminosity. The Sun is a G-type main sequence star, yellow-white, middle-aged, thoroughly ordinary. It has been burning hydrogen for about 4.6 billion years. It has roughly 5 billion years of hydrogen fuel remaining. In stellar terms, the Sun is a steady, reliable, profoundly boring object. And that is precisely why life was able to evolve on the planet orbiting it. Stability is what biology needs. Now consider a star born with 40 times the mass of the Sun, not 40% more, not 4 times more, 40 times more. Such a star does not merely burn brighter, it burns with a ferocity that defies easy comprehension. The relationship between a star's mass and its luminosity is not linear. It follows a steep power law, roughly proportional to the mass raised to the power of 3.5. A star with twice the mass of the Sun does not shine twice as bright. It shines roughly 11 times as bright. A star with 10 times the mass of the Sun shines approximately 32,000 times brighter. And a star with 40 times the mass of the Sun can shine 300,000 times brighter or more. This ferocious luminosity means it consumes its nuclear fuel at a vastly accelerated rate. The Sun has enough hydrogen in its core to sustain fusion for about 10 billion years. A star 40 times its mass might exhaust the same fuel in 3 to 4 million years. That is 1/2500th of the Sun's lifespan. It is like comparing a candle that burns for a full year to one that gutters out in 3.5 hours. Let us put this in perspective with a scaled comparison. If the entire lifespan of the Sun, 10 billion years, were compressed into a single calendar year, starting on January 1st and ending on December 31st, then our Sun would currently be in late July, roughly halfway through its life. It would have billions of simulated years stretching ahead of it, all the way through autumn and deep into winter. A star like WR124 on this same calendar would be born, live and die entirely within the first 3 hours of January 1st. By the time the clock struck 4 in the morning on New Year's Day, the massive star would already be gone, exploded, scattered, reduced to a dense remnant and an expanding cloud of debris. Meanwhile, the Sun would still have 364 ages and 20 hours left to live. That is the difference in timescale between an ordinary star and a stellar giant. The concept of a Wolf-Rayet star was first identified in 1867 by 2 French astronomers, Charles Wolf and Georges Rayet. working at the Paris Observatory. They had been conducting a systematic spectroscopic survey of stars, splitting their light into its component wavelengths using prisms and analyzing the resulting spectra for patterns. During this work, they noticed 3 stars in the constellation Cygnus, the Swan, that displayed unusually broad emission lines in their spectra. Most stars show narrow absorption lines, dark gaps in their rainbow of light caused by elements in the star's atmosphere absorbing specific wavelengths of light as it passes through. But these 3 stars were different. They showed bright, broad emission lines, spectral features that glowed rather than absorbed. This suggested that their outer atmospheres were not simply sitting quietly around the star. They were being violently expelled outward at tremendous speed. The gas was moving so fast that the emission lines were significantly broadened by the Doppler effect, the same phenomenon that makes an ambulance siren change pitch as it passes you. The faster the gas moves, the broader the lines appear. Wolf and Rayet did not fully understand what they had found. The physics of stellar evolution was still more than half a century away from being developed. It would take more than 100 years of painstaking observation and theoretical work before astronomers could explain what these peculiar stars truly were. We now know that Wolf-Rayet stars represent a late stage in the life of the most massive stars in the universe. When a star born with more than roughly 25 solar masses begins to exhaust its core hydrogen fuel, its evolution diverges sharply from the path taken by lower mass stars like our Sun. The Sun, when it exhausts its hydrogen in roughly 5 billion years, will swell into a red giant, expand to perhaps 100 times its current diameter, and then gently shed its outer layers to form a planetary nebula, leaving behind a white dwarf. The process is slow and comparatively gentle. A massive star does something fundamentally different. Its enormous luminosity, hundreds of thousands of times that of the Sun, drives powerful stellar winds that physically strip away the star's outer layers of hydrogen. These winds are driven by radiation pressure, the force exerted by photons of light as they interact with atoms in the star's atmosphere. In a massive star, the radiation pressure is so intense that it can accelerate gas to speeds of 1,000 to 3,000 kilometers per second. At such velocities, the mass loss is staggering. A Wolf-Rayet star can lose mass at a rate of roughly 10 to the negative 5th solar masses per year. Written differently, that is approximately 100,000th of the Sun's mass every year. That may sound like a small fraction, but remember that this rate is sustained over hundreds of thousands of years. Over the course of 300,000 years, the star sheds 3 solar masses. Over 1,000,000 years it sheds 10. Gradually, relentlessly, the wind strips the star down to its core, peeling away layer after layer of hydrogen-rich envelope and exposing the deeper layers where helium, carbon, nitrogen, and oxygen have accumulated from earlier stages of nuclear fusion. The hydrogen that once surrounded the star is gone, blown away into space, forming a vast nebula around the now naked stellar core. This is what makes Wolf-Rayet stars look so unusual in telescopes. Their spectra show the signatures of heavy elements, because we are essentially looking at the star's exposed innards. It is as if the star has been skinned alive by its own radiation, revealing the nuclear-processed material beneath. The surface temperature of a Wolf-Rayet star can exceed 40,000 degrees Celsius, with some reaching 100,000 degrees or more. Compare that to the Sun's surface temperature of 5,500 degrees. A Wolf-Rayet star's surface is between 7 and 18 times hotter than our Sun. The radiation pouring off these stars is so intense that it ionizes the gas surrounding them for light years in every direction, creating glowing emission nebulae that can be observed across vast distances. WR-124 sits approximately 15,000 light-years from Earth, in the direction of the constellation Sagittarius, the Archer. 15,000 light-years is a distance that resists human comprehension. Light travels at roughly 299,792 kilometers per second, or about 186,000 miles per second. In 1 year, a beam of light covers approximately 9.5 trillion kilometers. Multiply that by 15,000, and you arrive at the distance to WR-124. It is roughly 142 quadrillion kilometers away. These numbers are so large that they lose all meaning without comparison to something tangible. Here is a way to feel the distance. If you could drive a car at highway speed, 100 kilometers per hour, non-stop, day and night, without ever stopping for fuel or rest, it would take you approximately 160 billion years to reach WR124. The current age of the universe is only 13.8 billion years. You would need more than 11 times the current age of the universe to complete the journey at highway speed. That single fact should make clear just how vast the gulf of space truly is. And yet, by galactic standards, WR124 is a neighbour. It sits within our own spiral arm of the Milky Way, relatively close to us in the grand structure of the galaxy. Here is another scaled comparison. If the entire Milky Way galaxy, which spans roughly 100,000 light-years in diameter, were shrunk down to the size of a standard dinner plate, about 25 centimeters across, then WR124 would be a microscopic speck of dust about 3.8 centimeters from the plate's center. Our Sun would be another speck, approximately 6 centimeters from the center. On this scale, the two stars would be separated by about 2 to 3 centimeters, close enough to touch with your fingertip. Yet that tiny gap on the dinner plate represents 15,000 light-years of empty space. A void so immense that light itself needs 150 centuries to cross it. Wolf-Rayet stars are further divided into subtypes based on their spectral features. WN stars show prominent nitrogen lines, indicating that the star's surface is enriched in nitrogen from the carbon-nitrogen-oxygen cycle of hydrogen burning. WC stars show prominent carbon lines, indicating that helium-burning products have been exposed. WO stars, the rarest subtype, show oxygen lines, indicating even deeper layers have been stripped bare. WR124 is classified as a WN8 star, meaning it is a nitrogen sequence Wolf-Rayet star in one of the later spectral subtypes. This classification tells astronomers that the star has shed enough of its hydrogen envelope to reveal nitrogen-enriched material, but has not yet stripped down to the carbon-rich layers produced by helium burning. It is, in evolutionary terms, still in the earlier stages of the Wolf-Rayet phase. The star itself is estimated to have a current mass of about 20 to 30 times the mass of the Sun, though it was likely born with significantly more, perhaps 40 solar masses or greater. The difference between its birth mass and its current mass, 10 to 20 solar masses of material, represents the gas and dust it has already shed into space over the course of its life. That material forms the nebula M167, the glowing cloud that surrounds WR124 and that the James Webb Space Telescope imaged with such stunning clarity. M167 is not just large, it is structured. It has clumps and filaments and knots of compressed material arranged in patterns that reveal the history of the star's mass loss. Each clump is a chapter in the story of how this star has been destroying itself. Let us now talk about the telescope that made this observation possible. The James Webb Space Telescope, often abbreviated JWST, is the most powerful and complex space observatory ever built by human beings. It was launched on December 25, 2021, a Christmas morning gift to astronomy, aboard an Ariane 5 rocket from the Guiana Space Center in French Guiana on the northeast coast of South America. The telescope's primary mirror is 6.5 meters in diameter, composed of 18 hexagonal segments, each about 1.3 meters across, coated in a thin layer of gold approximately 100 nanometers thick. Gold is used because it is an excellent reflector of infrared light, which is the primary wavelength range that JWST is designed to observe. The mirror is so precisely shaped that the maximum deviation from the ideal surface across all 18 segments is less than 25 nanometers, roughly 1,000th the width of a human hair. JWST orbits the Sun at a point called the second Lagrange point, or L2, approximately 1.5 million kilometers from Earth, roughly 4 times the distance from the Earth to the Moon. At this location, the combined gravitational forces of the Earth and Sun, together with the orbital dynamics of the telescope, allow JWST to maintain a stable position relative to Earth with minimal fuel expenditure. A massive sun shield, roughly the size of a tennis court, keeps the telescope's instruments perpetually in shadow, cooling them to operating temperatures below 233 degrees Celsius. This extreme cold is essential because the telescope must detect infrared light, which is essentially heat radiation. If the telescope itself were warm, its own thermal emissions would overwhelm the faint signals from distant cosmic objects. By cooling the instruments to just a few tens of degrees above absolute zero, JWST can detect the infrared glow of objects billions of light years away. JWST carries four main scientific instruments. NIRCam, the near-infrared camera, captures images in near-infrared wavelengths between 0.6 and 5 micrometers. NIRSpec, the near-infrared spectrograph, splits the light of objects into spectra for detailed chemical analysis. MIRI, the mid-infrared instrument, observes at longer wavelengths between 5 and 28 micrometers, detecting heat radiation from cooler objects and cosmic dust. And FGS NIRIS, the fine guidance sensor and near-infrared imager and slitless spectrograph, provides ultra-precise pointing capability and additional spectral observations. It was MIRI, the mid-infrared instrument, that proved most transformative for the WR124 observation. Dust grains emit most strongly in mid-infrared wavelengths. By observing at these wavelengths, MIRI could reveal the detailed structure and distribution of dust in the nebula M167 in ways that no previous telescope, including Hubble, could achieve. The Hubble Space Telescope had observed WR124 years earlier. In 1998, Hubble captured images of M167 using its wide-field planetary camera, showing the clumpy, irregular structure of the ejected material. Those images were groundbreaking at the time. They revealed that the nebula was far from smooth, containing dense knots and shells of material that suggested episodic mass ejection. But Hubble primarily observes in visible and near-ultraviolet light. At those wavelengths, dust is difficult to study in detail. It does not glow brightly in visible light. It absorbs visible light, blocking our view of objects behind it, but it does not emit it. To see the dust itself, you need to observe in infrared, and that is precisely what JWST was designed to do. The resulting image, released publicly in March 2023 as part of a set of early science observations, showed the nebula M167 in breathtaking detail. Intricate filaments of dust radiated outward from the central star, like the tendrils of some enormous cosmic creature. Dense knots of material were embedded within the broader nebula structure, each one a dense concentration of gas and dust that has resisted dispersal by the stellar wind. Shells and arcs of compressed gas trace the history of past ejection events, like tree rings recording years of growth and hardship. The central star itself blazed with fierce intensity, its ultraviolet radiation ionizing the surrounding gas and creating a cavity of hot, low-density plasma around it. The dust was distributed in a complex pattern, neither smooth nor random, but structured in ways that encoded information about the physics of the stellar wind and its interaction with the surrounding interstellar medium. The comparison between the Hubble image from 1998 and the JWST image from 2022 was dramatic. Where Hubble saw a rough, clumpy glow, JWST revealed exquisite detail. Where Hubble could hint at the presence of dust, JWST could measure it directly. The infrared view transformed a known object into an essentially new discovery. Astronomers who had studied M167 for years described the JWST image as revelatory, a word scientists do not use lightly. The level of structural detail visible in the dust distribution exceeded what theoretical models had predicted. The nebula was more complex, more textured, more rich in features than anyone had anticipated. Wolf-Rayet stars are divided into several subclasses based on their spectral characteristics, reflecting different stages of chemical exposure as the star sheds its outer layers. WN-type Wolf-Rayet stars show prominent nitrogen emission lines, indicating that the surface material is dominated by products of the carbon-nitrogen-oxygen cycle, the fusion process that converts hydrogen to helium in massive stellar cores. WC-type Wolf-Rayet stars show strong carbon and oxygen lines, indicating that the star has shed even more material, exposing deeper layers where helium has been fused into carbon and oxygen. WO-type stars are the rarest of all, showing strong oxygen emission, suggesting that they are extremely evolved and nearing the end of their lives. WR124 is classified as a WN8 star, meaning it falls into the nitrogen-rich category and is relatively early in the Wolf-Rayet phase compared to WC and WO stars. Its spectrum is dominated by emission lines of ionized nitrogen and helium. This classification tells us that WR124 has stripped away its hydrogen envelope, but has not yet peeled down to the carbon-rich layers beneath. It is partway through the Wolf-Rayet phase, with further evolution yet to come. The luminosity of WR124 is estimated at roughly 150,000 times the luminosity of the Sun. If you could stand on a hypothetical planet at the same distance from WR124 as Earth is from the Sun, the radiation from the star would be so intense that it would vaporize not just any life but the planet itself. The stellar wind emanating from WR124 has a terminal velocity of roughly 700 km per second, slower than some other Wolf-Rayet stars, but still fast enough to traverse the distance from the Earth to the Sun in less than 2.5 days. This wind carries with it a steady stream of nitrogen-enriched material, gas that was once buried deep inside the star and has now been dredged up to the surface and expelled into space. The nebula M167 was first catalogued in 1966 by the astronomer Carl Henize during a survey of emission line objects in the southern sky. Its irregular, clumpy morphology puzzled observers for decades. Some early studies suggested it might be a planetary nebula, the shell of gas expelled by a dying low-mass star. But the connection to WR124, established through subsequent spectroscopic and kinematic studies, made clear that it was something very different. It was a wind-blown nebula, shaped by the outflow from a living star rather than the gentle death of a small one. Studies of the nebula's expansion velocity, roughly 150 km per second, combined with its angular size on the sky, suggest that the material in the outer parts of the nebula was ejected roughly 20,000 to 50,000 years ago. This is recent in stellar terms. The nebula is a fresh wound, still expanding, still glowing. What made this image so important was not merely its beauty, it was the data embedded within it. Each pixel of a JWST image carries spectral information that can reveal the composition, temperature, density, and velocity of the material being observed. For WR124, this meant that astronomers could study the dust being produced by the star's fierce winds in unprecedented detail. They could measure how much dust was present, what it was made of, how hot it was, and where it was concentrated. And what they found raised profound questions about one of the most persistent puzzles in astrophysics. Where does cosmic dust actually come from? How quickly can it form? And do stars like WR124 play a far larger role in seeding the universe with the raw materials of planets and life than anyone had previously calculated? These questions have haunted astrophysics for decades. The dust problem, as some researchers call it, is one of those deceptively simple puzzles that, the deeper you look, the more complicated it becomes. We see dust everywhere in the universe. We see it in nearby galaxies. We see it in galaxies so distant that their light has been traveling for more than 12 billion years. We see more dust than our models can easily explain. And WR124, this single dying star, captured in infrared by a telescope orbiting 1.5 million kilometers from Earth, may hold part of the answer. But before we can appreciate the significance of those discoveries, we need to understand something more fundamental. We need to understand why this star is dying at all, what its death will look like, and why the physics of stellar death is far stranger and more violent than most people realize. Because the fate of WR124 is not merely the end of one star. It is a preview of one of the most powerful events in the known universe. And what scientists discovered about the dust surrounding this star was more troubling and more exciting than anyone expected. Stars do not choose to die. They are forced to die by the laws of physics. Every star that has ever existed, from the first generation born in the primordial aftermath of the Big Bang to the youngest protostars forming today in the dark interiors of molecular clouds, is engaged in the same fundamental struggle. Gravity wants to crush the star into the smallest possible point. Nuclear fusion in the star's core generates the energy and radiation pressure needed to resist that crushing force. As long as there is fuel to burn, the star survives. When the fuel runs out, gravity wins, always, without exception. The manner in which gravity wins, however, depends almost entirely on how much mass the star had when it was born. And it is this dependence on mass that determines the difference between a quiet death and a cataclysmic one. For small stars like our Sun, the end is relatively gentle. When the Sun exhausts the hydrogen in its core, roughly 5 billion years from now, the core will contract and heat up, igniting hydrogen fusion in a shell surrounding the inert helium core. This shell burning will cause the outer layers of the Sun to expand enormously, swelling the star into a red giant roughly 100 times its current diameter. The outer edge of the Sun will extend beyond the current orbit of Mercury and possibly Venus. Earth may or may not be engulfed, depending on how much mass the Sun loses during this expansion. Eventually, the core will become hot enough to ignite helium fusion, converting helium into carbon and oxygen. But the Sun does not have enough mass to ignite carbon fusion. When the helium is exhausted, the core contracts one final time, and the Sun's outer layers are gently expelled into space, forming a glowing planetary nebula. The core that remains is a white dwarf, a dense remnant about the size of Earth, but containing roughly half the Sun's original mass. A white dwarf produces no energy through fusion. It simply cools over billions of years, gradually fading from white to yellow to red to brown to black, like an ember dying in a cosmic fireplace. No explosion, no shockwave, just a slow, quiet dimming. For massive stars, the story is catastrophically different. A star born with more than roughly 8 to 10 solar masses does not end as a white dwarf. It ends in a supernova, a titanic explosion that briefly outshines an entire galaxy containing hundreds of billions of stars. But the path from a living massive star to a supernova is not a simple one. It involves a series of increasingly desperate nuclear reactions, each one shorter and more frantic than the last, as the star burns through progressively heavier elements in a futile attempt to stave off the inevitable gravitational collapse. This is the situation WR-124 finds itself in right now. It has already exhausted the hydrogen in its core. That phase of its life ended long ago, perhaps hundreds of thousands of years ago. The hydrogen that remains in its outer layers has been blown away by the stellar wind, which is why it appears as a Wolf-Rayet star in the first place. After hydrogen, the star began infusing helium into carbon and oxygen in its core. This phase is shorter than the hydrogen burning phase by a large margin. For a star of WR-124's original mass, helium burning might last a few 100,000 years, perhaps 500,000 at most. After helium is exhausted, the core contracts further, temperatures rise to approximately 800 million degrees Celsius, and carbon begins to fuse into neon, sodium, and magnesium. Carbon burning lasts perhaps 1,000 years. Then neon burning begins, lasting roughly a year. Then oxygen burning, lasting a few months. Then silicon burning, the final stage, lasting approximately a single day. Think about that progression carefully. A star spends millions of years burning hydrogen, the majority of its life, then hundreds of thousands of years on helium, then 1,000 years on carbon, then a year on neon, then a few months on oxygen, then a single day on silicon. Each stage is shorter than the last by orders of magnitude. The acceleration is relentless and irreversible. To put this another way, imagine the entire post-main sequence evolution of a massive star as a clock counting down. The hydrogen burning phase is the first 999 out of 1,000 ticks. The helium burning phase is the last tick. And within that final tick, carbon, neon, oxygen, and silicon burning happen in the last fraction of a second. The star spends almost its entire life in a state of apparent stability, burning hydrogen peacefully, and then races through the final stages of its evolution in what amounts to an instant. An astronomer observing such a star at a random moment in its life would almost certainly catch it during the hydrogen burning phase. Catching it during the carbon or later phases would require extraordinary luck or an extraordinarily large survey. The fact that WR-124 has already moved past hydrogen burning and is in the Wolf-Rayet phase tells us it is already in the final fraction of its life. But we cannot tell from outside the star exactly which tick of the final clock it is on. It is like watching someone sprint toward the edge of a cliff, running faster and faster with each step, legs pumping harder and harder, unable to stop, unable to slow down, fully aware that the edge is approaching and that nothing, absolutely nothing, can prevent the fall. The laws of physics are the cliff. Gravity is the ground below. At the end of silicon burning, the core of the star is composed almost entirely of iron, and iron is where the road ends. Every nuclear fusion reaction up to this point has been exothermic, meaning it releases more energy than it consumes. Fusing hydrogen into helium releases energy. Fusing helium into carbon releases energy. Fusing carbon into neon, neon into oxygen, oxygen into silicon, silicon into iron. All of these reactions release energy. But fusing iron into heavier elements does not release energy, it absorbs energy. Iron sits at the peak of the nuclear binding energy curve. Its nucleus is the most tightly bound of all elements. To fuse iron into anything heavier requires pouring energy in rather than getting energy out. The star has reached a dead end. It has been burning through its fuel supply with increasing desperation, each new fuel lasting a shorter time than the previous one, and now there is nothing left to burn. The iron core grows as silicon burning continues in a shell around it. When the core reaches a critical mass, approximately 1.4 solar masses, a threshold known as the Chandrasekhar limit, named after the Indian-American astrophysicist Subrahmanyan Chandrasekhar, who calculated it in the 1930s, the pressure of degenerate electrons. The quantum mechanical force that has been supporting the core is no longer sufficient to resist gravity. The core collapses. What happens next takes less than a single second. The iron core collapses at roughly 1/4 the speed of light, approximately 75,000 kilometers per second. In a fraction of a second, a time interval shorter than the blink of an eye, the core compresses from a sphere roughly the size of Earth, about 12,000 kilometers in diameter, to a sphere roughly 20 kilometers across. The density in this collapsed core reaches values beyond anything we encounter in ordinary experience, beyond anything most human minds can genuinely comprehend. A single teaspoon of neutron star material, the stuff that the collapsed core becomes, would weigh approximately 6 billion tons on the surface of the Earth. To put that in perspective, 6 billion tons is roughly the weight of every building, every vehicle, every ship, every aircraft, every bridge, and every piece of infrastructure in a mid-sized country, all compressed into a volume smaller than a sugar cube. If you could somehow scoop out a teaspoon of this material and drop it onto the surface of Earth, it would punch through the planet's crust and mantle like a bullet through tissue paper. The outer layers of the star, which had been supported by the energy generated by nuclear fusion in the core, suddenly find themselves unsupported. The floor has been pulled out from beneath them. They come crashing inward, drawn by gravity toward the newly formed neutron star at the center. This infalling material slams into the surface of the neutron star at a significant fraction of the speed of light, perhaps 10 to 20% of 300,000 kilometers per second. The resulting bounce, combined with an enormous flood of neutrinos released by the neutronization of the core, where protons and electrons are crushed together to form neutrons, drives a powerful shock wave outward through the star. This shock wave tears the star apart from the inside out. The explosion is a core collapse supernova, one of the most violent events in the universe. The energy released in this event is almost beyond the capacity of mathematics to convey in human terms. A typical core collapse supernova releases approximately 10 to the 46 joules of energy in neutrinos alone. That is a 1 followed by 46 zeros. To grasp the scale of this number, consider that the total energy output of the Sun over its entire 10 billion year lifetime is roughly 10 to the 44 joules. A single supernova, in a matter of seconds, releases more energy in neutrinos alone than the Sun will produce in its entire existence, by a factor of 100. The visible light output of the supernova, the part we can observe with telescopes, represents roughly 1% of the total energy budget. But even that 1% is staggering. It is enough to make the exploding star shine with the luminosity of roughly 10 billion suns for several weeks. Here is a scaled comparison that may help convey the violence of this event. If a standard firecracker represents the energy output of a nuclear weapon, then a nuclear weapon represents roughly 1/4 of the energy of a supernova. The ratio between a firecracker and a supernova is greater than the ratio between a single bacterium and the entire Earth. These comparisons fail almost as much as they succeed, because at a certain point the numbers become so extreme that comparison itself breaks down. But the core point remains. A supernova is not merely a large explosion. It is an event that operates at the very limits of what physics allows. If a supernova occurred at the distance of Alpha Centauri, the nearest star system to our Sun at 4.2 light-years, it would be visible in broad daylight, brighter than the full moon, and would cast sharp shadows on the ground at night. If it occurred at the distance of Sirius, about 8.6 light-years away, it would still be clearly visible during the day and would dominate the night sky for weeks. Fortunately, there are no stars massive enough to produce supernovae within a few dozen light-years of Earth. The nearest candidate, Wolf-Rayet Star, and the nearest supernova progenitor in general, is far enough away to pose no direct threat to our planet. WR-124 is 15,000 light-years away, far enough that a supernova at its location would not pose a direct threat to Earth. The radiation and particles from the explosion would be diluted by the vast distance, but it would be a spectacular observational event, visible to the naked eye as a new star appearing in the constellation Sagittarius, possibly bright enough to be seen during daylight hours, depending on the geometry and energy of the explosion. More importantly, the supernova of WR-124 would provide an unprecedented opportunity for astronomers to study the death of a Wolf-Rayet star with the full array of modern instruments. JWST could observe the explosion in infrared. Ground-based telescopes could track it in visible light. Neutrino detectors buried deep underground could catch the flood of neutrinos from the core collapse. Gravitational wave observatories like LIGO and Virgo could potentially detect the ripples in space-time produced by the asymmetric collapse of the core. The data from such an event would be scientifically priceless. But here is the problem. We do not know when WR-124 will explode. The uncertainty is not a matter of decades. It could be a matter of millennia or even longer. The star could explode tomorrow. It could explode in 10,000 years. It could, under certain evolutionary scenarios, persist for another 100,000 years. The uncertainty is enormous because we cannot directly observe the nuclear reactions happening in the star's core. The core is hidden beneath the dense stellar wind, buried under layers of hot opaque plasma that no telescope can penetrate. We can measure the star's surface temperature, its luminosity, its mass loss rate, its spectral characteristics, and its position on theoretical evolutionary tracks. But the core, where the critical nuclear burning is taking place, is invisible to us. We are essentially trying to predict when a bomb will detonate by examining the color and texture of its outer casing. We can make educated guesses, we can run computer simulations, but we cannot know with certainty. The best estimates, based on stellar evolution models calibrated to the observed properties of WR-124, place the star somewhere in the later stages of its post-main sequence evolution. It has clearly shed most of its hydrogen envelope, which is why it appears as a WN-type Wolf-Rayet star. Some models suggest it may be in the core helium-burning phase, which would give it hundreds of thousands of years remaining. Other models, depending on the assumed mass loss rate and internal mixing processes, suggest it could be further along, perhaps in the carbon-burning or even neon-burning phase. If it is burning carbon, it has perhaps a few thousand years. If it is burning neon, it has roughly a year. If it is burning oxygen, it has months. If it is burning silicon, it has a single day. The difference between these scenarios, from the perspective of human observation, is the difference between a distant event that our descendants might witness and an event that could happen before this video finishes playing. We simply do not know which scenario is correct, and it gets worse. The type of supernova that WR-124 will produce is expected to be a type Ib or type IC supernova, classifications defined by the absence of hydrogen and sometimes helium lines in the explosion spectrum. Type Ib supernovae lack hydrogen lines because the progenitor star has already shed its hydrogen envelope before the explosion. Type IC supernovae lack both hydrogen and helium lines, indicating even more extreme stripping. Since Wolf-Rayet stars have already lost their hydrogen, and in some cases their helium envelopes, Their supernovae naturally fall into these stripped envelope categories. But some Wolf-Rayet explosions may be far more extreme. There is growing evidence that certain Wolf-Rayet stars, particularly those with rapid rotation rates and strong internal magnetic fields, can produce a hypernova, an explosion roughly 10 to 100 times more energetic than a standard supernova. The additional energy comes from the rotational energy of the collapsing core, which can be channeled into two narrow, relativistic jets of matter and radiation that punch through the star along its rotation axis. If these jets happen to be pointed toward Earth, we observe them as gamma-ray bursts, the most energetically luminous events in the known universe. A single gamma-ray burst can release as much energy in 10 seconds as the Sun will produce in its entire 10 billion year lifetime. The gamma-ray photons arrive in a brief, intense flash, followed by an afterglow that fades over hours to weeks as the jet decelerates and the emitting region expands. Long-duration gamma-ray bursts, those lasting more than about 2 seconds, are believed to originate almost exclusively from the collapse of rapidly rotating massive stars, potentially including Wolf-Rayet stars. Whether WR124 has the rotation rate and magnetic field strength to produce a gamma-ray burst when it finally explodes is a question we simply cannot answer with current technology. The star's rotation cannot be measured with current instruments at this distance. Its internal magnetic field configuration is entirely hidden from us behind the opaque stellar wind. We can only wait, observe, and calculate probabilities based on population statistics of Wolf-Rayet stars and gamma-ray burst progenitors. There is a certain unsettling quality to this ignorance. We know that WR124 will explode. We know that the explosion will be spectacular. We know that it could happen at virtually any time. But we do not know when, and we do not know exactly what kind of explosion it will be. It is like living next to a volcano that you know will erupt, but not knowing whether the eruption will be a gentle lava flow or a catastrophic blast. The uncertainty is inherent to the physics of the situation. Some things cannot be known until they happen. What we can study, however, is what the star is doing right now, and what it is doing right now is extraordinary. WR124 is producing dust. Not a little dust, not a trace amount detectable only with the most sensitive instruments. Enormous quantities of dust visible in rich, textured detail in the JWST infrared image. And this dust is one of the most significant and potentially paradigm-shifting discoveries to come from the early JWST science program. To understand why this matters so profoundly, we need to step back and ask a question that seems simple on its surface, but turns out to be one of the most challenging and consequential puzzles in modern astrophysics. The question is this: where does cosmic dust come from? Cosmic dust is not the dust you find under your bed or on a bookshelf. It consists of tiny solid particles, typically ranging in size from a few nanometers to a few micrometers, smaller than the diameter of a human hair by factors of 10 to 100. These particles are composed of silicates, carbon compounds, iron, magnesium oxide, and other refractory materials. Dust plays a critical role in the universe that extends far beyond its modest size. It is the raw material from which rocky planets form. It provides the solid surfaces on which complex molecules, including the precursors to amino acids and other organic compounds, can assemble through surface chemistry. It shields the interiors of molecular clouds from ultraviolet radiation, allowing those clouds to cool and collapse gravitationally into new stars and planetary systems. Dust absorbs starlight at visible wavelengths and re-emits it in infrared, profoundly affecting our observations of distant galaxies. Without dust, the universe as we know it, including Earth and every living thing upon it, could not exist. Dust is not a minor character in the cosmic story. It is a central player, a catalyst without which the transformation from simple gas to complex worlds and living organisms could never have occurred. But here is the puzzle, and it is a profound one. We can measure the total amount of dust in galaxies, both in the nearby universe and at high redshift, meaning we can observe galaxies as they appeared billions of years ago, when their light first began its journey toward us. And the amount of dust we observe, particularly in young galaxies in the early universe, is far greater than what existing models of dust production can account for. The traditional source of cosmic dust is the outflow from aging low to intermediate mass stars, particularly stars in the asymptotic giant branch phase, known as AGB stars. These are stars that have exhausted both the hydrogen and helium in their cores, developing a layered internal structure with a degenerate carbon-oxygen core, surrounded by a helium-burning shell, surrounded by a hydrogen-burning shell, surrounded by a vast, cool, distended envelope. The outer atmosphere of an AGB star is so cool, with temperatures around 2000 to 3000 Kelvin, that molecules can form. Silicon monoxide, aluminum oxide, titanium oxide, carbon monoxide, and many other molecular species condense in the dense outflow from the star's surface. These molecules serve as the nucleation sites for dust grains, tiny solid particles that grow by accreting additional atoms and molecules as they travel outward through the stellar wind. Over hundreds of thousands of years, an AGB star can shed most of its envelope, enriching the surrounding interstellar medium with freshly formed dust grains. AGB stars are excellent dust factories. They are the most thoroughly studied source of dust in the local universe. Observations at infrared and submillimeter wavelengths have catalogued thousands of dust-producing AGB stars in the Milky Way and its satellite galaxies. The chemistry of dust formation in AGB atmospheres has been modeled in considerable detail. Carbon-rich AGB stars produce soot-like carbonaceous dust. Oxygen-rich AGB stars produce silicate dust, similar in composition to common sand. The physics is well understood, and the models work well for explaining the dust we see in the present-day Milky Way. But AGB stars have a fundamental limitation that no amount of modeling can overcome. They are slow. A star of 1 solar mass takes roughly 10 billion years to reach the AGB phase. A star of 2 solar masses takes about 1 billion years. Even a star of 5 solar masses, near the upper end of the intermediate mass range, requires at least 80 to 100 million years to evolve to the AGB. In the early universe, just 300 to 800 million years after the Big Bang, the first generation of stars had only recently formed and begun to die. There simply had not been enough time for a significant population of AGB stars to form, evolve through the main sequence, ascend the giant branch, and begin producing dust. Yet we observe dust. We observe enormous amounts of it. The evidence comes from multiple independent observations. The Atacama Large Millimeter Array, or ALMA, a network of 66 radio antennas spread across the Atacama Desert in Chile, at an altitude of 5,000 meters, has detected thermal emission from cold dust in galaxies at redshifts above 6. The Herschel Space Observatory, a European Space Agency mission that operated from 2009 to 2013, surveyed hundreds of distant galaxies in far-infrared wavelengths, detecting dust masses that, in some cases, exceeded 100 million solar masses. These are not tentative or marginal detections. They are robust measurements confirmed by multiple instruments and cross-checked against independent datasets. The dust is there, the quantity is large, and the AGB stars have not had time to produce it. Something is wrong with our assumptions. This is not a phrase astrophysicists use lightly. It means that the standard framework, the accepted model for how dust is produced and distributed in the universe, does not match the observations. Either the models are missing a source of dust, or the known sources are far more efficient than current estimates suggest, or there is a mechanism at work that we have not yet identified. This discrepancy is sometimes called the dust budget crisis, and it has been a persistent source of frustration and fascination in observational cosmology for more than 20 years. Wolf-Rayet stars offer a potential way out. Unlike AGB stars, massive stars evolve rapidly. A star born with 40 solar masses can reach the Wolf-Rayet phase in just 3 to 4 million years. If Wolf-Rayet stars produce significant quantities of dust during their brief, violent existences, they could help explain the unexpectedly high dust abundances in the early universe, where only short-lived massive stars had had time to evolve. But until the JWST observation of WR124, the observational evidence for dust production in isolated, solitary Wolf-Rayet stars was limited and ambiguous. Most of the known dust-producing Wolf-Rayet stars were in binary systems, where the collision of two powerful stellar winds creates a compressed, high-density interaction zone where temperatures drop and dust nucleation can occur. The famous Pinwheel Nebula around the binary Wolf-Rayet system WR104 is a spectacular example. In this system, two massive stars orbit each other with a period of roughly 220 days. Where their winds collide, a dense shock region forms. As the binary pair orbits, this shock region sweeps around like a cosmic lawn sprinkler, leaving behind a beautiful spiral pattern of dust that has been imaged from the ground using adaptive optics at the Keck Observatory in Hawaii. The system earned the nickname Apep, after the serpent deity of Egyptian mythology, because of the serpentine curves of its dust plume. But the dust in WR104 exists precisely because there are two stars. The binary interaction creates conditions that a single star cannot replicate on its own, or so it was believed. WR124 challenges this assumption directly. It appears to be a single star. Extensive spectroscopic monitoring over many years has revealed no evidence of radial velocity variations that would indicate a companion star in a close orbit. While it is always possible that a faint, low-mass companion exists at a wide separation, such a companion would not produce the wind collision region needed to drive binary dust formation. If WR124 is truly solitary, and the evidence strongly suggests it is, then the dust in M167 must be forming through a fundamentally different mechanism. The wind itself must be creating conditions favourable for dust nucleation, without any external assistance. This is a much harder problem from a physics standpoint. A single Wolf-Rayet wind is hot, fast, and bathed in intense ultraviolet radiation from the star. These are hostile conditions for dust survival, let alone dust formation. Yet the JWST image shows that dust is there, in abundance, in complex, structured formations that cannot be explained by anything other than active, ongoing production. But here's what makes this truly terrifying. The amount of dust that JWST detected around WR124 is not a marginal quantity. The nebula M167 contains dust structures extending across several light-years, glowing brightly in mid-infrared wavelengths, arranged in complex filaments and clumps that suggest active, ongoing dust formation within the stellar wind. If this process is common among solitary Wolf-Rayet stars, and if even a fraction of the nearly 600 known Wolf-Rayet stars in our galaxy are producing dust at similar rates, then the total contribution of Wolf-Rayet stars to the Milky Way's dust budget, and by extension to the dust budgets of galaxies across the universe, may be far greater than any previous model had predicted. The implications ripple outward from one star to encompass the entire history of cosmic chemistry. And those implications demand that we look more carefully at the theories and models that scientists have built over decades of research to explain where cosmic dust comes from and how it gets distributed throughout the universe. Because each of those models, taken alone, has strengths and weaknesses. Each explains part of the puzzle, but leaves gaps that the others must fill. And the JWST observation of WR124, a single image of a single star, has the potential to shift the balance between these competing theories in ways that reverberate across multiple fields of astrophysics, from stellar evolution to galaxy formation to the origins of planets and life. The problem is not that we have too few explanations. The problem is that none of them, alone or in combination, has yet provided a fully satisfactory account of the dust we observe. And each new observation, each new piece of data, has a way of complicating the picture rather than simplifying it. The JWST image of WR124 is no exception. It has answered some questions, yes, but it has raised others that are, if anything, even more challenging. And to understand those questions, we need to examine the major theories one by one, with the honesty and rigor they deserve, acknowledging both their power and their limitations. But before we do, one final point about the significance of dust that is easy to overlook. Without dust, there are no rocky planets. Without rocky planets, there is no stable surface on which liquid water can pool. Without liquid water and a stable surface, the complex prebiotic chemistry that led to the first self-replicating molecules on Earth could not have occurred. Dust is not merely an astronomical curiosity. It is a prerequisite for our existence. Every grain of dust in the nebula of WR124 is a potential building block of a future world. The question of where dust comes from is, in a very direct sense, the question of where we come from. And the answer, as we are about to see, is more complex and more contested than you might expect. The question of where cosmic dust originates has driven decades of research across multiple fields of astrophysics. It is one of those problems that sits at the intersection of stellar physics, interstellar chemistry, galaxy evolution, and cosmology, drawing insight and frustration from each discipline in roughly equal measure. To understand why the JWST image of WR124 matters so deeply, we need to examine the major theories and approaches that scientists have pursued over the past several decades and honestly assess why each one, taken alone, falls short of providing a complete explanation for the dust we observe in the universe. The first and most established proposed source of cosmic dust, as we discussed, is the asymptotic giant branch star. Let us now look at this source more carefully. AGB stars undergo thermal pulses, periodic surges of energy from the helium-burning shell that lies between the degenerate carbon-oxygen core and the hydrogen-burning shell. These thermal pulses drive convection in the outer envelope, dredging up carbon and other fusion products from the interior and enriching the surface chemistry. The enriched surface material is then expelled by the stellar wind, which in AGB stars is driven primarily by radiation pressure on dust grains that have already formed in the cool upper atmosphere. This creates a beautiful feedback loop. Dust forms near the star's surface. Radiation pushes on the dust drags gas along with it. The outflow carries more material away from the star, which cools further and forms more dust. The process is self-sustaining and efficient. The dust production rate in AGB stars can be substantial. A typical carbon-rich AGB star produces dust at a rate of roughly 10 to the -7th to 10 to the -6 solar masses per year. Over the roughly 500,000 years that an AGB star spends on the giant branch, it can produce a total dust mass of perhaps 10 to the -2 to 10 to the -1 solar masses, depending on the star's initial mass and metallicity. Multiply this by the number of AGB stars in a galaxy, and the total contribution is significant. In the Milky Way today, AGB stars are thought to be the dominant source of stardust, producing perhaps 2/3 of all new dust entering the interstellar medium. But the limitation is the one we have already identified: timescale. The universe is 13.8 billion years old today, which gives plenty of time for low-mass stars to reach the AGB phase. But at a redshift of 7, the universe was only about 750 million years old. At a redshift of 8, roughly 650 million years old. The first stars, the so-called population 3 stars, likely formed about 100 to 200 million years after the Big Bang. By the time the universe was 700 million years old, only stars with masses above roughly 5 solar masses could have completed their evolution and reached the AGB or post-AGB phase. Lower mass stars, the 1 to 3 solar mass stars that are the most abundant and the most prolific dust producers, would still be on the main sequence, happily burning hydrogen, millions or billions of years away from producing any dust at all. The AGB source simply runs out of time in the early universe. The second major candidate is supernovae, and specifically the dust that forms in the cooling ejector after a core collapse supernova explosion. When a massive star explodes, the ejector contains substantial quantities of heavy elements: oxygen, silicon, magnesium, iron, carbon, synthesized during the star's life and during the explosion itself. As the ejector expand and cool over months and years, conditions in certain regions of the expanding debris become favorable for molecules to form and dust grains to nucleate. The first clear observational evidence for dust formation in supernova ejector came from supernova 1987A, the brightest supernova visible from Earth since Kepler's supernova in 1604. Located in the Large Magellanic Cloud, at a distance of approximately 168,000 light-years, supernova 1987A has been monitored continuously since its discovery in February 1987, providing an unprecedented record of how a supernova evolves over decades. Early observations showed evidence of dust formation within the first 2 years after the explosion, as the infrared luminosity of the remnant increased while the optical luminosity declined, consistent with newly formed dust grains absorbing visible light and re-emitting it at longer wavelengths. but the amount of dust detected in those early years was modest, perhaps 10 to the negative 4 to 10 to the negative 3 solar masses. That was disappointing for models that needed supernovae to be major dust sources. Then, 20 years later, observations with the Herschel Space Observatory at far infrared wavelengths revealed much more dust than the early measurements had suggested. The cold dust deep inside the remnant, shielded from the hottest regions by the surrounding ejector, had been invisible at shorter wavelengths. Herschel measured a total dust mass of roughly 0.5 to 0.8 solar masses, a factor of hundreds to thousands larger than the early estimates. Follow-up observations with ALMA confirmed this result, detecting cold dust emission from the inner ejector and constraining the dust mass to roughly half a solar mass. This was a watershed moment. It meant that a single supernova could produce a significant quantity of dust, enough to matter for the cosmic dust budget. The story of supernova 1987A illustrates both the promise and the frustration of supernova dust research. For 2 decades after the explosion, astronomers believed that the dust production was modest. The early infrared measurements, taken within the first few years, consistently showed small dust masses. Papers were published arguing that supernovae were minor dust sources, incapable of explaining the dust abundances in distant galaxies. Theoretical modelers adjusted their frameworks accordingly, assigning a small contribution to supernovae and looking elsewhere for the missing dust. Then Herschel came along with its far-infrared vision and revealed that the dust had been hiding in plain sight, or rather hiding in plain cold. The cold dust deep inside the remnant was invisible at the shorter wavelengths used in the early observations. It took a telescope specifically designed to detect cold dust emission to find it. This episode is a cautionary tale for all of dust astrophysics. What we do not observe, we tend to assume does not exist. But absence of evidence, particularly when our instruments have limited sensitivity or wavelength coverage, is not evidence of absence. How many other supernovae are harboring cold dust that our current instruments cannot detect? How many other stellar sources are producing dust that we have not yet been able to measure? The JWST observation of W124 belongs to this same narrative tradition, a new instrument revealing what previous instruments had missed. If every core collapse supernova produced half a solar mass of dust, the supernova source could potentially close the dust budget gap in the early universe. Core collapse supernovae come from massive stars that evolve rapidly, so they are available even in young galaxies. The formation rate of massive stars was likely high in the early universe, driven by the elevated star formation rates observed in early galaxies. So the combination of rapid evolution and high formation rates could, in principle, produce enough dust to match the observations. But here's the problem. The same shockwave that drives the supernova explosion also destroys dust. As the expanding blast wave sweeps through the surrounding interstellar medium, it heats existing dust grains to thousands of degrees, vaporizing them through thermal sputtering. And within the remnant itself, a reverse shock forms when the expanding ejecta encounter the surrounding medium and bounce back inward. This reverse shock plows back through the ejecta, heating and destroying the very dust grains that formed in the cooling aftermath of the explosion. The net dust production of a supernova, the amount that actually survives to enter the interstellar medium, depends on the balance between formation in the expanding ejecta and destruction by the reverse shock. The numbers here are deeply uncertain, and that uncertainty is the crux of the problem. Some theoretical models predict that the reverse shock destroys 80 to 90% of the newly formed dust, leaving only 10 to 20% to survive and contribute to the interstellar medium. Other models, using different assumptions about grain sizes, compositions, and the density of the surrounding medium, predict higher survival rates of 40 to 60%. The difference matters enormously. If the survival rate is 90%, then supernovae are prolific net dust producers and may account for most of the dust in the early universe. If the survival rate is only 10%, then supernovae produce only a modest trickle of net dust, and the budget crisis remains as acute as ever. The key variables are the grain size distribution and the density of the medium into which the remnant expands. larger grains survive shock waves better than smaller grains because their greater mass-to-surface area ratio makes them harder to heat and erode. If the dust formed in supernova ejecta is predominantly composed of large grains, say a tenth of a micrometer or larger, the survival fraction could be high. If the grains are predominantly small, a few nanometers across, the survival fraction could be very low. Observations of supernova 1987A suggest that the grains are large, consistent with the high dust masses inferred from Herschel and ALMA data. But 1987A is a single event. Whether its grain properties are representative of core collapse supernovae in general is not known. The density of the surrounding medium also matters, because it determines how quickly the reverse shock forms and how strongly it interacts with the inner ejector where the dust resides. In a low-density environment, such as the interior of a stellar wind bubble, the reverse shock forms late and is relatively weak. In a high-density environment, the reverse shock forms early and is strong, potentially destroying more dust. Wolf-Rayet stars, by virtue of their powerful winds, clear out large cavities in the surrounding medium before they explode. This means that the supernova from a Wolf-Rayet progenitor may expand into a relatively low-density cavity, which could favor dust survival. This is another connection between the pre-supernova wind phase and the post-supernova dust budget, a connection that the study of WR-124 and its nebula M167 is helping to elucidate. As of today, this question is not settled. The survival rate of supernova-formed dust is one of the most important and most poorly constrained parameters in all of dust astrophysics. The third approach to solving the dust budget problem involves grain growth in the interstellar medium. This idea takes a fundamentally different approach to the problem. Rather than requiring stellar sources to produce all the dust directly, it proposes that stars only need to produce small seed grains, tiny nucleation sites a few nanometers across, and that these seeds then grow much larger by accreting gas phase atoms of carbon, silicon, iron, and other elements as they drift through the dense interiors of molecular clouds. This process, called accretion or mantle growth, is supported by both theoretical models and some observational evidence. In dense molecular clouds, where gas densities are high and temperatures are low, the timescale for grain growth can be relatively short, perhaps a few tens of millions of years, much shorter than the billion-year timescales required for AGB star evolution. The appeal of this model is considerable. It relaxes the requirement on stellar dust sources. It can operate at any cosmic epoch, as long as there is a supply of gas phase metals and dense cloud environments. And it is consistent with observations showing that dust grains in the interstellar medium are, on average, larger than dust grains freshly produced by stellar sources, suggesting that some growth has occurred after the grains left their parent stars. However, the model has important limitations. Grain growth requires a supply of gas phase metals, which means it depends on prior stellar nucleosynthesis and enrichment. In the very early universe, at redshifts above 6 or 7, the interstellar medium had low metallicity. The total abundance of elements heavier than helium was much smaller than it is today. With fewer atoms available in the gas phase, grain growth is slower and less efficient. Models that rely heavily on grain growth struggle to explain the most distant, most metal-poor galaxies where dust has been detected. The process also competes with grain destruction by supernova shockwaves, creating a delicate balance that depends on the supernova rate, the density structure of the interstellar medium, and the efficiency of atom-grain sticking collisions in ways that are extremely difficult to constrain observationally. There is a further subtlety to the grain growth model that deserves attention. Not all environments are equally conducive to grain growth. The dense interiors of molecular clouds, where hydrogen densities can reach 10,000 to 1 million particles per cubic centimeter, are the most favorable sites. In these cold, dense environments, the timescale for a grain to double its mass through accretion can be as short as 10 million years. But the diffuse interstellar medium, where densities are typically 1 to 10 particles per cubic centimeter, is far less hospitable. Grains spend much of their time drifting through this diffuse medium, where growth rates are negligibly slow. Only when a grain enters a molecular cloud, perhaps swept up by the compression of a passing spiral arm or drawn in by the gravitational collapse of a gas cloud, does rapid growth resume. The fraction of time that grains spend in dense environments versus diffuse environments is therefore a critical parameter, one that varies from galaxy to galaxy and from epoch to epoch. Furthermore, grain growth is not a permanent acquisition. Grains that grow mantles in molecular clouds can have those mantles removed when they are subsequently exposed to energetic radiation from newly formed stars or to shock waves from nearby supernovae. The cycle of growth and destruction, deposition and sputtering, accretion and erosion, creates a dynamic equilibrium in which the total dust mass in a galaxy reflects the balance between all of these competing processes. Getting this balance right in a theoretical model requires tracking the life histories of individual grains as they move through the complex, turbulent, multi-phase interstellar medium. This is a formidable computational challenge, and different research groups, using different numerical methods, have arrived at different conclusions about how effectively grain growth can supplement stellar dust sources. The fourth candidate source, and the one that the JWST observation of WR124 has brought into sharp focus, is dust production in the winds of Wolf-Rayet stars. We have already discussed the basic physics of Wolf-Rayet winds, their extreme velocities, high mass loss rates, and enrichment in heavy elements. The question is whether and how efficiently these winds can form dust. The traditional view held that dust formation in Wolf-Rayet winds is rare and inefficient, largely restricted to binary systems where wind-wind collision creates favorable conditions. This view was supported by the observational record. The majority of confirmed dust-producing Wolf-Rayet stars were in binaries. Solitary Wolf-Rayet stars, when observed at infrared wavelengths, generally showed little or no evidence of dust emission, but the traditional view may have been a product of observational limitation rather than physical reality. Ground-based infrared telescopes, and even the Spitzer Space Telescope, which preceded JWST and operated from 2003 to 2020, had limited angular resolution and sensitivity at the wavelengths where warm dust emits most strongly. Spitzer's primary mirror was only 85 centimeters in diameter, less than 1/8 the diameter of JWST's mirror. Its angular resolution at mid-infrared wavelengths was correspondingly lower. It could detect large, bright dust features around the most luminous Wolf-Rayet stars, but might miss smaller, fainter, or more diffuse dust structures around less extreme objects. Ground-based telescopes face an even more fundamental obstacle. Earth's atmosphere absorbs most mid-infrared radiation, limiting ground-based observations to a few narrow windows of partial transparency. Even through those windows, the thermal emission from the atmosphere itself creates a bright foreground that drowns out faint astronomical signals. Only a space-based telescope, operating above the atmosphere and cooled to cryogenic temperatures, can achieve the sensitivity needed to detect subtle dust features around distant stars. JWST, with its 6.5-meter mirror, its operating temperature below 50 Kelvin, and its suite of sensitive mid-infrared detectors, represents a quantum leap in our ability to observe cosmic dust. The observation of WR124 demonstrated this powerfully. Where Hubble and Spitzer saw hints of dust, mere suggestions in the data that could be interpreted in multiple ways, JWST saw a rich, detailed, unmistakable landscape of dust structures extending across the entire nebula. The improvement was not incremental, it was transformational. Features that had been invisible were now obvious. Structures that had been hypothetical were now measured. The debate shifted from whether there was dust to how much, what kind, and what it meant. There is also the question of what happens to the dust after it leaves the immediate vicinity of the star. The stellar wind of WR124 is not expanding into a vacuum. It is expanding into the interstellar medium, the thin gas that fills the space between stars. When the fast-moving wind encounters this slower-moving ambient gas, a shock front forms. At this boundary, the wind material is compressed and heated, potentially destroying some of the dust grains that had formed further inward. The structure of M167 reflects this interaction. The outermost edges of the nebula show evidence of compression and heating where the wind meets the interstellar medium. The inner regions, closer to the star but shielded from the shock by intervening material, appear to contain the highest concentrations of dust. This spatial distribution carries implications for the ultimate fate of the dust. Grains that form deep within the wind and are then carried outward may pass through the shock front and be partially or completely destroyed. Grains that form further from the star, in regions where the wind has already slowed and cooled, may be better positioned to survive and escape into the interstellar medium. Understanding the radial distribution of dust formation within the wind, which regions produce dust and which regions destroy it, is essential for calculating the net dust output of the star. The JWST data provide the spatial resolution needed to begin addressing this question, but a full answer will require combining the imaging data with spectroscopic observations that can measure the temperature, density, and velocity of the gas at different distances from the star. The numbers are striking. The MIRI observations of WR-124 detect dust emission at wavelengths of 7.7, 10, 11.3, 12.8, 15, 18, and 21 micrometers, spanning a wide range of the mid-infrared spectrum. The brightness and spatial distribution of this emission are consistent with dust temperatures of roughly 200 to 300 Kelvin, significantly warmer than typical interstellar dust at 15 to 25 Kelvin, but cooler than the gas in the stellar wind. The total mass of dust in M167 has not been precisely determined from the JWST data alone, as this requires careful modeling of the grain size distribution, composition, and optical properties. But preliminary estimates suggest a dust mass of at least several thousandths of a solar mass, possibly more. If this dust was produced over the roughly 20 to 50,000 year lifetime of the nebula, the implied dust production rate is on the order of 10 to the negative 7 to 10 to the negative 6 solar masses per year, comparable to the dust production rates of AGB stars. This is a critical point. If solitary Wolf-Rayet stars produce dust at rates comparable to AGB stars, but evolve on timescales 1,000 times shorter, then Wolf-Rayet stars could be significant dust sources in the early universe where AGB stars are not yet available. Even if their per-star dust contribution is modest, their rapid evolution means they can begin contributing dust within just a few million years of star formation, providing an early source of solid-phase material that AGB stars cannot match. How is the dust forming in the hostile environment of WR-124's wind? The leading explanation involves the inherently clumpy nature of the stellar wind. Theoretical models of radiation-driven winds, particularly the work developed from the pioneering Castor, Abbott, and Klein formalism of 1975 and its subsequent refinements, predict that line-driven winds are inherently unstable. A process called the line deshadowing instability causes small perturbations in the wind to grow, creating dense clumps embedded within a more rarefied, fast-moving interclump medium. These clumps can be 10 to 100 times denser than the average wind density. Within the interior of a dense clump, the ultraviolet radiation field from the star is attenuated by the clump's own opacity. The interior is shielded from the destructive photons that would otherwise prevent dust formation. Temperatures within the shielded region can drop to levels where carbon, silicon, and other refractory elements can condense into solid grains. This clumpy wind dust formation mechanism does not require a binary companion. It is intrinsic to the physics of the wind itself, and it has been studied theoretically for decades, though until the JWST observation, direct observational confirmation in solitary Wolf-Rayet stars was elusive. The instability that produces clumps in radiatively driven winds is a subtle and fascinating piece of physics. In a smooth, steady wind, each atom in the outflow absorbs photons from the star's radiation field. The absorbed photon transfers momentum to the atom, pushing it outward. But if a small region of the wind becomes slightly denser, through a random fluctuation, it absorbs more photons from below because the material beneath it, which would normally absorb some of those photons, has been slightly thinned by the perturbation. This means the dense region accelerates faster than its surroundings, pulling away from the material behind it and sweeping up the material ahead of it. The perturbation amplifies itself. Dense regions get denser, thin regions get thinner. Within a few stellar radii, the originally smooth wind has broken up into a collection of dense shells and clumps, separated by regions of low density, fast-moving gas. Numerical simulations of this process, beginning with the work of Iwaki, Castor and Rybicki in the late 1980s, and refined by many groups since, consistently produce winds with density contrasts of 10 to 100 between clumps and interclump regions. The clumps occupy a small fraction of the total volume, but contain a large fraction of the total mass. They are the dominant structures in the wind, and their properties, size, density, spacing, and velocity, determine many of the observable characteristics of Wolf-Rayet stars, including their spectral line profiles, their X-ray emission, and, crucially, their ability to form dust. The dense interior of a clump is a fundamentally different environment from the hot, tenuous interclump gas. While the interclump medium may have temperatures of millions of degrees, heated by shock interactions between colliding flow regions, the interior of a dense clump can cool efficiently through radiative emission. If the clump is dense enough and large enough, its core can reach temperatures of just a few thousand Kelvin, cool enough for refractory molecules like carbon monoxide and silicon carbide to form. These molecules serve as nucleation sites for dust grains, which then grow by accreting additional atoms from the surrounding gas. It predicts that dust should form in discrete locations within the wind, concentrated in the dense clumps, rather than uniformly throughout the entire outflow. And this is exactly what the JWST image shows. The dust in M167 is not smoothly distributed. It is concentrated in clumps, knots, and filaments, precisely the structures that the clumpy wind model predicts. The correspondence between theory and observation is compelling, though far from conclusive. More observations of more Wolf-Rayet stars will be needed to confirm whether this mechanism is general or specific to WR124. There is a fifth perspective that attempts to synthesize all of the above into a unified framework. Perhaps the solution to the dust budget crisis is not a single source, but a combination of sources, each contributing at different rates during different cosmic epochs. In the very early universe, within the first few 100 million years after the Big Bang, the dust budget may have been dominated by core collapse supernovae and Wolf-Rayet winds, both of which arise from massive stars that evolve in just a few million years. These fast-acting sources provide the initial seeds of dust that allow molecular clouds to cool and fragment, enabling the next generation of star formation. In the intermediate age universe, from roughly 1 to 5 billion years after the Big Bang, grain growth in the interstellar medium begins to supplement the stellar sources, building up the total dust mass beyond what the stars alone could produce. And in the mature universe, from 5 billion years onward, AGB stars join the mix in force, eventually becoming the dominant source as the accumulated population of low and intermediate mass stars reaches the giant branch and begins shedding dust-enriched envelopes at high rates. Each epoch has its own dominant source. Each source has its own strengths and weaknesses. And the total dust mass at any given time reflects the cumulative contributions of all sources that have operated up to that point, minus the dust destroyed by supernova shockwaves and other energetic processes. This composite model has been explored in computational simulations of galaxy evolution by research groups at several institutions, including the University of Copenhagen, the University of Groningen, and University College London, among others. These simulations track the birth, evolution, and death of individual stellar populations within a modelled galaxy, calculating the dust production and destruction rates at each tamipep, and summing the results to predict the total dust mass as a function of cosmic time. The results are encouraging, but not definitive. Some simulations can reproduce the observed dust masses in early galaxies if they include generous contributions from supernovae and rapid grain growth. Others struggle even with these assumptions, falling short of the highest dust masses observed at redshifts above 6. The introduction of Wolf-Rayet dust production as a significant new term in these models is still in its early stages. The JWST observation of WR124 was published only recently, and the full implications have not yet been incorporated into most galaxy evolution codes. When they are, the results may change substantially. Even a modest increase in the assumed dust production rate per Wolf-Rayet star could have a significant cumulative effect over the millions of Wolf-Rayet stars that have existed across cosmic history. This composite model has the advantage of flexibility. It does not require any single source to do all the work. It allows different sources to dominate at different times, depending on the star formation history, metallicity, and density conditions of each galaxy. But it also has the disadvantage of complexity, with multiple free parameters, including the efficiency of each dust source, the survival rates of dust in supernova shockwaves, the timescales for grain growth, and the role of galactic winds in removing dust from galaxies entirely. The model becomes difficult to test against observations in a definitive way. Each observation can be accommodated by adjusting one or more parameters, which means the model is flexible but not necessarily predictive. The JWST observation of WR124 does not by itself resolve this debate, but it provides a crucial data point. It demonstrates, for the first time with high-resolution infrared imaging, that solitary Wolf-Rayet stars can be significant dust producers. This was previously a theoretical possibility. Now it is an observational fact, and that fact must be incorporated into every model of cosmic dust production going forward. The Wolf-Rayet contribution can no longer be treated as negligible or restricted to binary systems. It is real, it is measurable, and it may be widespread. The task ahead is to observe more Wolf-Rayet stars with JWST and its successors to determine how common dust production is among solitary objects, to measure the mass and composition of the dust being produced, and to incorporate these measurements into galaxy-scale models of chemical evolution. This is a multi-decade research program. It will require hundreds of hours of telescope time, sophisticated theoretical modeling, and careful comparison between observations and simulations. But the foundation has been laid. WR124 has shown us where to look and what to look for. The rest is the work of science. But before we leave this discussion, there is one more dimension to consider that ties all of the previous theories together. When WR124 eventually explodes as a supernova, the blast wave will sweep outward through the very nebula we see in the JWST image. It will encounter the dust that the star has spent tens of thousands of years producing. Some of that dust will be vaporized instantly, heated to temperatures of millions of degrees by the passing shock wave. But some of it, particularly the dust in dense clumps at the outer edges of the nebula, far from the epicenter of the explosion, may survive. Dense clumps resist destruction by shock waves because their high internal density and small cross-section relative to their mass make them harder to accelerate and harder to heat uniformly. The outer parts of a clump are ablated away by the shock, but the interior can remain relatively intact. If a meaningful fraction of the pre-supernova dust survives the explosion, it will be swept up into the expanding remnant and eventually injected into the surrounding interstellar medium. This surviving pre-existing dust could serve as seed material for subsequent grain growth in molecular clouds, accelerating the buildup of dust in the interstellar medium. In this scenario, the Wolf-Rayet wind phase and the supernova explosion are not separate, competing sources of dust. They are successive phases of a single integrated process. The wind produces the seeds, the supernova distributes them, the molecular clouds grow them to full size. This integrated view of dust production is one of the most exciting recent developments in the field. It recognizes that the dust cycle in a galaxy is not a set of independent, isolated events, but a continuous, interconnected process in which the output of one phase becomes the input of the next. The WR124 system, observed first in its wind phase by JWST, and perhaps one day in its supernova phase by whatever observatory succeeds JWST, could provide the first end-to-end observational test of this integrated dust production model. There is a haunting elegance to this possibility. A star born millions of years ago, burning through its fuel at a ferocious rate, stripping itself down to its exposed core, shedding dust into the void, and then, in a final cataclysmic moment, detonating with a violence that outshines galaxies. And out of that violence, the dust, some destroyed, some preserved, all of it scattered into the interstellar medium to begin the long, slow journey toward becoming part of a new world. It is destruction and creation locked in an unbreakable cycle, each dependent on the other, neither meaningful without the other. And that cycle is not abstract. It is happening now. It is happening 15,000 light-years away, in the wind of a dying star that does not know and cannot know that a species of upright primates on a small rocky planet has built a telescope and pointed it in exactly the right direction at exactly the right time to catch the process in action. The coincidence is not cosmic. It is us. We looked. We chose to look. And what we found is reshaping our understanding of how the universe manufactures the raw materials of existence. The dust being created around WR124 right now, at this very moment, will still be drifting through interstellar space long after every human being alive today has turned to dust themselves. The irony is exact and inescapable. There is a deeper truth hiding beneath the dust, the spectra, and the models. A truth that the JWST image of WR124 quietly reveals if you know where to look. It is a truth not about stars or dust or telescopes, but about us, about the relationship between the most violent processes in the universe and the most delicate structures we know of. The neurons firing in your brain as you read or listen to these words, the hemoglobin molecules in your blood carrying oxygen to your cells with each heartbeat, the calcium phosphate crystals in your bones, giving your skeleton its strength and structure. None of these things should exist. Not here, not now, not on this small rocky planet orbiting a modest yellow star in the suburbs of a spiral galaxy. Not without stars like WR124. To understand why, we need to go back to the beginning, not the beginning of WR124, the beginning of everything. In the first few minutes after the Big Bang, roughly 13.8 billion years ago, the universe was a cauldron of unimaginable heat and density. As it expanded and cooled, the fundamental particles condensed out of the primordial plasma, protons and neutrons formed. And within the first 3 minutes, nuclear reactions assembled those protons and neutrons into the nuclei of the lightest elements. Hydrogen, the simplest element consisting of a single proton, helium, with 2 protons and 2 neutrons, and trace amounts of lithium and beryllium, barely detectable against the overwhelming abundance of hydrogen and helium. That was all. The periodic table, which in its modern form contains 92 naturally occurring elements, was almost entirely empty. The universe was chemically barren. There was no carbon, no oxygen, no nitrogen, no silicon, no iron, no calcium, no phosphorus, no sulfur. None of the elements that make up the rocks beneath our feet, the water in our oceans, the air in our lungs, or the molecules in our cells. Everything heavier than helium, everything that astronomers collectively and somewhat misleadingly call metals, had to be created later. And the only factories in the universe capable of creating these elements were stars. Nuclear fusion in stellar cores builds elements up the periodic table in a stepwise fashion. Hydrogen fuses to helium. Helium fuses to carbon through the famous triple alpha process, one of the most delicate and improbable nuclear reactions in nature, a process so finely tuned that the physicist Fred Hoyle used its existence as evidence that the laws of physics must be compatible with the emergence of life. Carbon fuses to oxygen. Oxygen fuses to silicon. Silicon fuses to iron. Each step requires higher temperatures and pressures, and each step produces an element essential to the chemistry of life. The carbon in every organic molecule on Earth, the oxygen in every molecule of water, the silicon in every grain of sand, the iron in every red blood cell. The triple alpha process deserves special attention because it illustrates just how contingent our existence is on the precise properties of nuclear physics. For 3 helium nuclei, each containing 2 protons and 2 neutrons, to fuse into a single carbon nucleus requires 2 of them to first combine into an unstable beryllium nucleus, which decays in less than 10 to the negative 16 seconds. During that vanishingly brief window, a 3rd helium nucleus must collide with the beryllium and stick. This reaction would be hopelessly improbable were it not for a nuclear resonance, an energy level in the carbon nucleus that happens to be positioned at almost exactly the right energy to enhance the reaction rate by many orders of magnitude. Fred Hoyle predicted the existence of this resonance in 1953 on purely theoretical grounds. reasoning that without it, stars could not produce carbon, and without carbon, life as we know it could not exist. The resonance was subsequently discovered experimentally, exactly where Hoyle predicted it would be. The carbon in your body exists because of a coincidence in nuclear physics that Hoyle argued could not be a coincidence at all. But stellar fusion can only build elements up to iron. To create the elements heavier than iron, the gold, the silver, the platinum, the uranium, the thorium, and dozens of other elements, requires a different mechanism entirely. These heavy elements are forged in the extreme conditions of supernova explosions and neutron star mergers through a process called rapid neutron capture, or the R process. In the violent seconds during and after a core collapse supernova, free neutrons flood the atomic nuclei in the ejector, building them up to heavier and heavier isotopes faster than the nuclei can decay. The result is a burst of heavy element production that creates elements all the way up to and beyond uranium. Every atom of gold in every piece of jewelry on Earth was created in this way. Every atom of iodine in your thyroid gland, every atom of barium in the medical contrast agents used in hospital imaging. Let that sink in. The atoms in your body are not merely old, they are ancient beyond any human concept of time. They were forged in nuclear furnaces that burned millions of years ago, scattered into the void by explosions that outshone galaxies, drifted through interstellar space for eons, were gathered up by gravity into molecular clouds, compressed into a spinning disk around a young sun, accreted into a rocky planet, and eventually, after 4.5 billion years of geological and biological evolution, assembled themselves into the precise configuration that is you. You are not merely observing the universe, you are the universe observing itself. The atoms in your body have histories that stretch back billions of years, through multiple generations of stellar birth, nuclear burning, explosive death, and rebirth. WR-124 is part of this chain. Right now, at this very moment, it is engaged in one of the key steps of the cosmic recycling process. The mass it is shedding into space through its fierce stellar wind contains carbon, nitrogen, oxygen, and other heavy elements, elements that were synthesized in its core by nuclear fusion and then dredged up to the surface by powerful convective currents. The dust forming in the wind is the physical embodiment of this element dispersal. Each dust grain is a tiny package of heavy elements, wrapped in a solid matrix of silicates, or carbonaceous material, ready to be delivered to the interstellar medium. When WR-124 eventually explodes as a supernova, the blast will add even more heavy elements to this cosmic delivery, including elements that can only be produced in the extreme conditions of the explosion itself, elements created by the R process in the seconds after the core collapses. This is not science fiction. This is not speculation or metaphor. This is measured, observed, quantified reality, confirmed by decades of spectroscopic analysis, isotopic measurements, and computational modeling. The JWST image of WR-124 is not showing us something exotic or alien. It is showing us the process by which the universe creates the conditions for complexity. Without this process, there would be no rocky planets. Without rocky planets, there would be no liquid water pooling on surfaces under stable atmospheres. Without liquid water and a stable energy source, there would be no biochemistry as we know it. Without biochemistry, there would be no life. Without life, there would be no consciousness. Without consciousness, there would be no one to build a golden mirror and point it at a dying star 15,000 light-years away and wonder what it means. The chain is unbroken. It stretches from the first generation of massive stars that formed a few 100 million years after the Big Bang, through billions of years of stellar evolution, supernova explosions, nebula condensation, and planetary formation, all the way to the moment you are experiencing right now. And WR-124 is one of its links. There is another aspect of the JWST observation that deserves careful attention, an aspect that has received less public discussion than the dust itself, but that carries profound implications for our understanding of stellar physics. The image revealed not just that dust exists around WR-124, but how the dust is distributed in space. The nebula M167 does not have a smooth, spherical structure. the kind of shape you might expect if a star were shedding mass uniformly in all directions at a constant rate. Instead, the nebula is lumpy, clumpy, and asymmetric. Some regions are dense with dust, packed into bright knots and filaments. Others are relatively empty, dark voids where the wind has apparently blown clear. The clumps are not randomly distributed. They follow patterns that suggest the stellar wind has been interacting with the surrounding interstellar medium in complex ways, creating hydrodynamic instabilities and turbulence that shape the flow of ejected material into the structures we see. This structure is not merely beautiful. It carries information, quantitative, analyzable, scientifically valuable information. The size, spacing, density, and composition of the clumps tell us about the physics of the wind, the mass loss history of the star, and the properties of the surrounding interstellar medium. By analyzing the detailed structure of M167, astronomers can reconstruct the history of WR124's mass loss over the past 10,000 to 50,000 years. Each clump is like a geological stratum, a record of a specific epoch in the star's recent history. A dense knot of material may represent a period when the mass loss rate surged, perhaps triggered by a change in the star's internal structure as it burned through a new nuclear fuel. A gap between clumps may represent a period of relative calm. Together, the clumps form a timeline of the star's behavior, written not in ink and paper but in dust and gas. What this timeline reveals is that the mass loss from WR124 has not been steady. It has varied significantly over time. There have been episodes of enhanced ejection when the star shed material at a higher rate, creating dense shells and knots, and there have been quieter periods when the mass loss rate dropped and the wind was less dense. This variability is consistent with theoretical models of Wolf-Rayet stellar evolution, which predict that the mass loss rate should change as the star transitions between different nuclear burning phases and as its internal structure evolves. A transition from helium burning to carbon burning, for example, would alter the star's luminosity, radius, and surface temperature, all of which affect the properties of the radiation-driven wind. The JWST data provide the most detailed observational confirmation of this variability in any solitary Wolf-Rayet star to date. Previous observations with Hubble and ground-based telescopes could see the broad outlines of the nebula structure, but lacked the sensitivity and angular resolution to resolve the fine details. JWST's MIRI instrument, with its ability to detect thermal emission from warm dust at multiple wavelengths, has transformed M167 from a blurred portrait into a high-resolution autobiography. A telescope orbiting the Sun 1.5 million kilometers from Earth, built by human hands over a span of more than 2 decades, has captured an image detailed enough to reveal the episodic mass loss history of a star 15,000 light-years away. The clumps in the nebula are not just pretty features in an infrared photograph. They are data points. They are the star's autobiography, written in infrared light and read by a golden mirror the size of a tennis court. Let that sink in. The implications of this variability extend beyond the study of WR124 itself. If the mass loss rate from Wolf-Rayet stars is not constant, but varies over time, then the total mass shed by a given star during its Wolf-Rayet phase depends on the detailed history of that variability. Periods of enhanced mass loss produce denser clumps that may be more effective at forming dust, since the higher density provides better shielding from the star's ultraviolet radiation and more raw material for grain nucleation. Periods of reduced mass loss produce thinner, less dense outflows that may be less conducive to dust formation. The total dust production from a Wolf-Rayet star is therefore not simply a function of its average mass loss rate. It depends on the pattern of variability, the duty cycle of high and low mass loss episodes, and the physical conditions within each episode. This complexity makes it challenging to extrapolate from a single observation of a single star to the entire population of Wolf-Rayet stars in a galaxy. WR124 may be representative, or it may be unusual. Its current mass loss rate, its wind velocity, its chemical composition, its metallicity, all of these factors influence its dust production in ways that may differ from other Wolf-Rayet stars. What the JWST observation has done is demonstrate that the mechanism works in at least one case. The next step, already being planned by research teams around the world, is to observe additional solitary Wolf-Rayet stars to determine how common this dust production is. Every additional observation narrows the uncertainty. Every additional detection strengthens the case that Wolf-Rayet stars are a significant, previously underappreciated source of cosmic dust. The connection between this astrophysical research program and the fundamental question of our origins is direct and inescapable. If Wolf-Rayet stars produce significant quantities of dust in the early universe, they accelerate the formation of the next generation of stars and planets. More dust means more efficient cooling in molecular clouds, which means faster gravitational collapse, which means more stars forming per unit time, which means more planetary systems, which means more opportunities for the complex chemistry that leads to life. The dust around WR124 is not just interesting to astrophysicists. It is interesting to anyone who has ever looked up at the night sky and wondered whether there is anyone else out there looking back. There is a philosophical dimension here that is worth pausing to consider, even in a discussion grounded in observational science. We talk about cosmic dust as if it were merely a scientific curiosity, a puzzle to be solved, a parameter to be constrained in computational models of galaxy evolution. But dust is far more than that. Dust is the medium through which the universe transforms itself from simplicity to complexity. In the first few 100 million years after the Big Bang, the universe contained only hydrogen and helium, two elements, chemically simple, structurally featureless. There was nothing in the universe capable of forming a solid surface, a liquid, a crystal, a membrane, or a molecule more complex than hydrogen. Through the action of gravity, nuclear fusion, and stellar death, these two elements were transmuted into 92 naturally occurring elements, each with unique chemical properties, each capable of forming compounds and structures that hydrogen and helium alone could never achieve. Dust is the vehicle for this transformation. It is the physical embodiment of the universe's increasing chemical complexity. Each dust grain is a tiny laboratory where atoms of different elements are locked together in solid-state compounds, silicates, oxides, sulfides, carbon lattices, structures that preserve the products of stellar nucleosynthesis in a durable form that can survive the harsh conditions of interstellar space. When we look at the JWST image of WR124 and see those intricate filaments of dust glowing in the infrared against the black of space, we are not looking at debris. We are looking at the raw material of future worlds. Some of that dust will drift through interstellar space for millions of years, pushed by radiation pressure, tugged by gravity, swept along by the magnetic field of the galaxy. Some of it will eventually be swept up by the gravitational pull of a molecular cloud, a vast, cold, dense region of space where gas and dust accumulate under the influence of gravity. Within that cloud, the dust grains will collide with gas molecules, cooling the gas and allowing it to collapse further. A protostar will form at the center of the collapsing region. A disk of gas and dust will form around it, spinning faster as it contracts, like a figure skater pulling in their arms. Within that disk, the dust grains will collide with each other, sticking together through van der Waals forces and electrostatic attraction, gradually building up from nanometer-scale particles to micrometer-scale grains, to millimeter-scale aggregates, to centimeter-scale pebbles, through a process that is still not fully understood, called pebble accretion or streaming instability. These small bodies will assemble into kilometer-scale planetesimals. Planetesimals will collide and merge into protoplanets. Protoplanets will clear their orbits and become planets. And on one of those planets, if conditions are right, the heavy elements delivered by stars like WR124 will participate in chemistry complex enough to give rise to self-replicating molecules, molecules that can copy themselves, molecules that can evolve, life. We are not separate from this process. We are its product. We are made of atoms that were once inside stars. The dust surrounding WR124 right now, at this very moment, contains atoms that may one day be part of a living organism on a world that does not yet exist. WR124 is not merely a star in the sky. It is one of the engines that drives the process that made us possible, and the JWST image is the most detailed snapshot we have ever taken of that engine in action. Consider one more scaled comparison to grasp the magnitude of what we are discussing. The entire mass of Earth is approximately 6 times 10 to the 24 kilograms, or about 3/millionths of the Sun's mass. The dust in M167 has not been precisely weighed by the JWST observations, but estimates based on the infrared brightness and spatial extent of the dust emission suggest it contains at least several Earth masses of solid material, possibly significantly more. This means that the dust blown off by a single Wolf-Rayet star, one star among roughly 400 billion in our galaxy, contains enough solid material to construct multiple rocky planets. Not gas giants like Jupiter and Saturn, rocky planets like Earth, worlds with solid surfaces, worlds with the potential for mountains and oceans and atmospheres and the complex chemistry that makes biology possible. There is something else worth considering. The JWST observation of WR124 is not the end of this story. It is the beginning of a new chapter in observational astrophysics. With the sensitivity and resolution demonstrated by this single observation, astronomers can now plan systematic surveys of other Wolf-Rayet stars, both solitary and binary, to determine how common dust production is among this rare but cosmically significant class of objects. Each new observation will add another data point to the emerging picture of Wolf-Rayet dust production. Each data point will help constrain the models, and each constraint will bring us closer to solving the dust budget crisis that has troubled cosmologists for decades. Future telescopes will push even further. The extremely large telescope, currently under construction in the Atacama Desert in Chile, will have a primary mirror 39 meters in diameter, roughly 6 times the diameter of JWST's mirror. It will observe in the near-infrared and mid-infrared with angular resolution far surpassing anything available today. When it turns its enormous eye toward Wolf-Rayet nebulae, it will resolve structures within the dust that JWST can only hint at. It will measure the composition and size distribution of individual dust clumps. It will track the motion of the ejected material over time, providing direct measurements of the wind velocity and mass loss rate. And if we are fortunate enough to witness the supernova of a well-studied Wolf-Rayet star during the operational lifetime of these instruments, we will be able to follow the entire process from dust production to dust destruction to dust dispersal in real time, providing the first complete observational record of a single star's contribution to the cosmic dust cycle. The scientific stakes could not be higher. Understanding where cosmic dust comes from is not an abstract academic exercise. It is directly connected to understanding how rocky planets form, how the building blocks of life are assembled, and whether the conditions for life are common or rare in the universe. Every answer we obtain about the dust around WR124 brings us closer to understanding our own origins. The JWST has not merely taken a photograph, it has captured, in a single infrared frame, the raw materials for a dozen possible worlds, still warm with the heat of their creation, still drifting outward from the star that forged them, still waiting to be gathered up by gravity and assembled into something new, something that might, in another 4 or 5 billion years, look up at a sky full of stars and wonder, as we do now, where it all came from. What does all of this mean? Not for astrophysics, not for the computational models and the spectral fitting routines and the dust opacity calculations. For us, for human beings living on a small rocky planet orbiting an ordinary star in a suburban arm of an ordinary spiral galaxy in an observable universe containing roughly 2 trillion galaxies. It means, first and most fundamentally, that we are deeply, inextricably embedded in a cosmic process that is far larger, far older, and far more powerful than anything in human experience. The elements that constitute our bodies were not created on Earth. They were not created in our solar system. They were created in the cores and explosions of stars that lived and died billions of years before our sun was born, dispersed into interstellar space by stellar winds like the one blowing off WR124 right now, and accumulated over cosmic timescales through the slow, patient, implacable work of gravity. We did not arise independently of the cosmos. We arose from it, we are made of it. We are, in a very real and physically measurable sense, the cosmos turned inward to examine itself. This is not a metaphor. It is not poetic license. It is a statement that can be verified by isotopic analysis. The calcium atoms in your skeleton were synthesized by nuclear fusion in a massive star that exploded before our sun was born. The specific isotopic ratios of calcium in your bones matched the predictions of supernova nucleosynthesis models. The iron atoms in your hemoglobin were the end products of silicon burning in a stellar core, created in the final day of a massive star's life. The phosphorus atoms in the backbone of your DNA, linking the nucleotides together in the double helix that carries the instructions for building every protein in your body, were created in supernova explosions, forged in conditions of temperature and density that would vaporize any planet. If you could trace the complete history of each atom in your body, each individual atom, you would find that it has a story stretching back billions of years, involving multiple stellar generations, each one contributing something new to the chemical richness of the galaxy. WR124 is part of the current chapter of this ongoing 13.8 billion-year-old story. It is a star in the active process of returning its heavy elements to the interstellar medium, preparing the raw materials for the next generation of stars and planets. The carbon, nitrogen, and oxygen in its wind will eventually become part of a molecular cloud. That cloud will collapse to form new stars. Around those stars, planets will form. And the elements that WR124 is scattering into space right now will become part of those new worlds. When it eventually explodes, the supernova will enrich the surrounding gas with fresh, heavy elements, increasing the metallicity of the local interstellar medium and providing the raw materials for future planetary systems. Some of the dust it has already shed may survive the explosion and be incorporated into a new planetary disk millions of years from now. There is a certain poignancy in this realization. We are temporary. Our lives are measured in decades, a span of time so brief that in cosmic terms it barely registers. The star WR124, violent and unstable as it is, has already lived for millions of years and will be remembered in the fossil record of the interstellar medium for billions more. The atoms that compose us will outlast us by timescales so vast they make the entire history of human civilization look like a momentary flicker. They were here long before us, cycling through stars and clouds and planets. And they will be here long after we are gone, participating in new combinations, new structures, new chemical possibilities. We are brief arrangements of matter, momentary patterns in an ongoing cosmic dance that began 13.8 billion years ago and will continue for timescales that make human civilization look like a single grain of sand on an infinite beach. If the entire history of the universe were compressed into a single calendar year, with the Big Bang occurring at midnight on January 1st, and the present moment falling at midnight on December 31st, then the first stars would form in the second week of January. The Milky Way would take shape in late January. Our Sun and solar system would form in early September. The first multicellular life on Earth would appear in mid-November. The dinosaurs would go extinct on December 26th. The entire history of Homo sapiens, every tool, every cave painting, every language, every civilization, every war, every scientific discovery, every work of art, every moment of love and loss and wonder, would occupy the final 14 seconds before midnight on December 31st. The life of WR124 would occupy a few seconds sometime on December 31st. The life of the Sun would span the last 5 weeks of the year, and the formation of the first atoms of hydrogen and helium, the raw material from which everything else was eventually built, would occur in the first 3 minutes of January 1st. We are latecomers to a universe that has been building complexity for a very long time, but we are not passive observers of this process. We are the products of it, and we carry within us the isotopic signatures of every stellar generation that contributed to the chemical enrichment of our region of the galaxy. When we point the James Webb Space Telescope at WR124 and study the dust in its wind, we are studying our own origins. We are reading the recipe for our own existence, written in infrared photons by a dying star. There is something remarkable about our particular moment in cosmic history. We are the first generation of living beings on this planet, and perhaps in this galaxy, to possess the technological capability to observe the dust production process in detail and to understand what we are seeing. For 4.5 billion years, Earth has orbited the Sun while stars like WR124 have been living and dying throughout the galaxy, producing the dust that eventually became part of our world. But until the launch of JWST, no instrument existed that could resolve the fine structure of Wolf-Rayet nebulae in the infrared. No telescope could reveal the clumps and filaments and knots of dust in M167 with the clarity we now possess. We are witnessing, for the first time in the history of life on Earth, the detailed mechanism by which the universe manufactures the raw materials of existence. Previous generations could theorize about this process. We can observe it directly. This observational capability carries a responsibility. The data from JWST is not merely archived on hard drives. It is being analyzed by research teams across the globe, incorporated into models of galactic chemical evolution, compared against theoretical predictions, and used to refine our understanding of processes that shape the habitability of the cosmos. The image of WR124 is not a curiosity to be admired and forgotten. It is a working document of science, a piece of evidence in an ongoing investigation that touches on the most fundamental questions humans have ever asked. Where did we come from? Are we alone? How common are the conditions for life in the universe? There is a second implication that deserves reflection. The JWST observation of WR124 reminds us that the universe is not static, not finished, not a completed work that we merely inhabit and observe. It is a process, ongoing and dynamic, with new stars forming in molecular clouds throughout the galaxy, old stars dying and returning their enriched material to the interstellar medium, dust being created in stellar winds and destroyed in supernova shockwaves, elements being synthesized and dispersed in an endless cycle that has been running for billions of years and will continue for billions more. The universe we inhabit today is not the same universe that existed a billion years ago, and it will not be the same universe a billion years from now. The chemical composition of the Milky Way is slowly but measurably changing as each generation of stars enriches the interstellar medium with heavier elements. Each successive generation of stars and planets is born from a slightly richer chemical mix than the generation before it. This means that the universe is, in a very real and quantifiable sense, evolving. Not in the biological sense of natural selection, but in the sense that its properties are changing over time in a directional way. It is becoming more chemically complex. It is producing more dust, more heavy elements, more of the raw materials needed for rocky planets, and the complex surface chemistry that, on at least one world we know of, gave rise to life. Whether this increasing complexity inevitably leads to life wherever conditions permit, or whether life is a rare accident that depends on an improbable conjunction of circumstances, remains one of the great open questions of 21st century science. But the trend itself is unmistakable. The universe is getting better at building the ingredients for life with each passing cosmic epoch. Stars like WR124 are the engines of that improvement. Consider the arithmetic of enrichment. The first generation of stars, born from primordial hydrogen and helium with essentially zero metallicity, could not have produced rocky planets. There was simply no silicon, iron, or oxygen available to form rocks. The second generation, enriched by the deaths of the first, had a trace of heavy elements, perhaps enough to form small, metal-poor rocky bodies. The third generation had more. The fourth more still. Our Sun is a relatively late generation star, born from gas that had been enriched by perhaps dozens of previous stellar generations over 9 billion years of galactic chemical evolution. The heavy element abundance of our solar system, roughly 2% by mass, represents the cumulative output of countless stars that lived and died before our Sun was born. Each Wolf-Rayet star that sheds its enriched material into the interstellar medium, each supernova that scatters its nucleosynthetic products across light years of space, incrementally increases the metallicity of the gas from which the next generation of stars will form. And here is a third implication, perhaps the most unsettling and the most beautiful. The JWST image of WR124 is, in one sense, a portrait of destruction. A star is tearing itself apart. Its mass is being scattered into the void. In a few thousand or a few 100,000 years, the star will cease to exist as a coherent object, replaced by a neutron star or a black hole and a rapidly expanding cloud of debris. This is, by any human measure, a catastrophe. An object that has existed for millions of years, that has burned with the intensity of 300,000 suns, will be obliterated in less than a second. But in cosmic terms, the destruction of WR124 is not an ending. It is a transformation. The death of this star is the creation of the raw materials for future worlds. The elements forged in its core over millions of years will be scattered across light years of space. The dust already drifting through its nebula will survive, in part, and seed the next generation of molecular clouds with the solid phase material needed to form planets. The supernova shockwave will compress surrounding gas, triggering new episodes of star formation that would not have occurred without the external push. Destruction and creation are not opposites in this context. They are partners. They are two faces of the same process, each dependent on the other, neither meaningful without the other. This duality, destruction and creation intertwined, is one of the deepest and most persistent themes in astrophysics. Stars must die for new stars to form. Elements must be forged in the furnaces of stellar cores and released by explosive death before they can be incorporated into planets and living organisms. The universe builds complexity through violence. It creates through destruction. And we, the products of this violent creativity, brief arrangements of atoms temporarily aware of their own existence, are here to witness it, to study it, to measure it, and to wonder at it. So here we are, on a small planet orbiting a quiet star in a galaxy of 400 billion suns. We have traveled together through the physics of stellar evolution, the chemistry of cosmic dust, the engineering of the most powerful telescope ever built, and the deep connections between the violence of stellar death and the existence of everything we know and everything we are. We began with a dying star, and we end with a universe in motion, a universe that builds worlds from the ashes of suns. 15,000 light-years away, WR124 continues its slow, magnificent self-destruction. Right now, as you read or listen to these words, the star's fierce wind is pouring mass into space at a rate that beggars comprehension. Dust grains are nucleating in the dense clumps of that wind, tiny solid particles condensing out of the hot gas like frost forming on a winter window, each one a package of heavy elements wrapped in a matrix of carbon or silicates. The nebula M167 is growing, its outer edge expanding into the interstellar medium, pushing against the ambient gas and dust of the galaxy, carving a cavity in the cosmic void. This star will die, that much is certain. The physics of nuclear burning guarantee it. The iron core that is being assembled, atom by atom, in the center of WR124 will one day reach the Chandrasekhar limit and collapse. The collapse will take less than a second. The resulting supernova will be visible across the galaxy, a new point of light appearing in the constellation Sagittarius, perhaps bright enough to read by at night. The shock wave will race outward at tens of thousands of kilometers per second, sweeping through the nebula we have spent this entire discussion examining, compressing and heating the surrounding gas and dust, destroying some of it, preserving some of it, and triggering new rounds of star formation in nearby molecular clouds that might otherwise have remained dormant for millions of years. The neutron star or black hole left behind will be a gravitational memorial in the fabric of space-time, a permanent record that something immense once existed in this exact location and burned with the fury of hundreds of thousands of suns. Over millions of years, the expanding remnant will merge with the interstellar medium, its identity gradually lost as the elements it contributed become part of the general chemical mix of the galaxy. But the story does not end with the explosion. It continues in the dust. It continues in the heavy elements scattered across light years of space. It continues in the molecular cloud that will eventually collect this material and collapse under its own gravity. It continues in the protostellar disk that will form around a new star, a disk containing ancient grains from WR124 mixed with material from dozens of other stellar sources, each contributing its own complement of elements to the mix. It continues in the planetesimals that will form within that disk, small rocky bodies assembling themselves from the collision and accretion of dust grains over millions of years. It continues in the planet that will form from those planetesimals, a world with a solid surface, a molten iron core generating a protective magnetic field, an atmosphere held in place by gravity, and perhaps, if the distance from the star is right, liquid water. On that world, the carbon atoms from WR124 might become part of an organic molecule. The oxygen atoms might become part of water. The nitrogen atoms might become part of an amino acid, one of the 20 building blocks that all known life uses to construct proteins. The iron atoms might settle into the planet's core, contributing to the dynamo that generates the magnetic field, shielding the surface from harmful cosmic radiation. The silicon atoms might become part of a grain of sand on a beach that no human being will ever see. And if conditions align, if the temperature is right, if liquid water persists for long enough, if the chemistry achieves sufficient complexity through billions of years of random combination and natural selection, something might stir on that world. Something might begin to replicate. Something might begin to evolve. We cannot know if this will happen. We cannot know if the specific atoms now being shed by WR124 will ever be part of a living organism. The probability for any individual atom is vanishingly small, but the process itself is not improbable. We know it happens because it happened here, on Earth, in our own solar system. The atoms that compose every living thing on this planet were once inside stars that died. The iron in your blood, the calcium in your bones, the carbon in your DNA, all of it passed through at least one stellar interior before arriving here. The process that is unfolding around WR124 right now is the same process that 4.5 billion years ago created the conditions for our existence, the same physics, the same chemistry, the same patient, violent, beautiful cycle of creation through destruction. There is a final thought that ties together everything we have discussed tonight. When JWST captured the image of WR124, the photons that struck the detector had been traveling for 15,000 years. They left the nebula when the last ice age was ending on Earth, when mammoths still roamed, the northern continents and human beings were painting bison on the walls of caves in what is now France and Spain. The light that revealed the dust around WR124 to us is older than agriculture, older than writing, older than civilization itself. By the time that light reached the golden mirror of JWST, the nebula it departed from had already changed. New clumps had formed, old clumps had dissipated. The star had shed additional mass. The dust structures we see in the image are ghosts, records of a moment that ended before recorded history began. We are always looking into the past when we look at stars. Every observation is archaeology. The universe is not indifferent to us, nor is it aware of us. It simply does what it does, following the laws of physics with perfect consistency, building complexity from simplicity, creating new possibilities from the destruction of old structures, cycling matter through stars and clouds and planets, in a process that has been running since the first generation of massive stars ignited a few 100 million years after the Big Bang. We are one of those possibilities, a temporary arrangement of atoms, a pattern of matter that has, through billions of years of evolution, acquired the remarkable and perhaps unique ability to understand its own origins. WR124 does not know we are watching, it cannot know. It is a sphere of plasma, 20 to 30 solar masses of incandescent gas, driven by nuclear physics and shaped by gravitational pressure, following a path determined by its mass, its composition, its angular momentum, and the unforgiving equations of stellar evolution. It has no awareness, no purpose, no intention. It simply burns, it simply sheds, it simply follows the laws of nature to their inevitable conclusion. But we know we are watching, and in that knowing, in that act of observation and comprehension and wonder, something extraordinary is happening. The universe, through us, is looking back at itself. The dust that will one day form new worlds is being studied by creatures made of the same kind of dust, creatures assembled from atoms forged in earlier generations of stars that died the same kind of death that WR124 is now approaching. We are the cosmos examining its own machinery. We are stardust contemplating stardust. We are the universe's way of understanding itself. And the image of WR124, that breathtaking portrait of a dying star surrounded by the glowing dust of its own unmaking, captured by a golden mirror orbiting the Sun at a distance of 1.5 million kilometers, is not just a scientific measurement. It is a mirror. It shows us where we came from. It shows us where the universe is going. It shows us that creation and destruction are not opposites but partners in an endless cycle that has been turning for 13.8 billion years and will continue turning for timescales that dwarf human comprehension. The star is dying, the dust is forming, new worlds are being seeded with the elements of existence, and somewhere, sometime, in a future we will never witness, the atoms being scattered by WR-124 may become part of something alive, something that opens its eyes for the first time, something that looks up at a sky it does not yet understand and wonders, as we wonder now, where it all began. The answer, as always, is the same. It began in the heart of a star. It always begins in the heart of a star,